Welcome back. We are continuing our example 11.8. So as we were just discussing, our volume of the water should equal the volume of the steel, okay, due to Archimedes' principle, okay. So let's go ahead and plug in our mass. It's going to be 1.0 times 10 to the 7th kilograms, okay. And our density of the steel, we should be able to find on this page, or maybe earlier in the chapter, 11.1. Yes, okay. So let's see. Steel, iron or steel, right there. This is going to be the density. 7.8 times 10 to the 3rd kilogram meters cubed. Okay, so we can put that in, 7.8 times 10 to the 3rd kilogram per meters cubed. And so we can use our calculator, 10 to the 7th over 7.8 times 10 to the 3rd. And we get 1.28 times 10 to the 3rd, and this is now in meters cubed, which is good. We found a volume. Okay? Now we can plug that in to our mass of the water. We know that the density of water is 10 to the 3rd kilogram per meters cubed, and then plug in our volume of the water there. Okay. So times 10 to the 3rd. That'll get us 1.28 times 10 to the 6th. Okay. And now this is just in kilograms. All right. So now our buoyant force is equal to that mass that we just found times 9.8 meters per second squared. Okay, so times 9.8, that gives us 1.26 times 10 to the 7th, and this is now in newtons. Okay, so this is our buoyant force. Okay. Now, if we want to compare that to our steel's weight, F steel is going to be our mass of the steel, which was given as 1 times 10 to the 7th, times our gravity, right? So mass of steel times gravity. So that gives us 9.8 times 10 to the 7th newtons. Okay, so comparing this buoyant force to the weight of the steel, okay, we see that the weight of the steel is larger than the buoyant force. Okay. Okay. So, what does that mean? This means that our force due to gravity of the steel is higher than the buoyant force, so it will overcome that buoyant force. Okay? Alright, so part B. What is the maximum buoyant force that water would exert on the same steel if it were shaped into a boat that could displace 1 times 10 to the 5th meters cubed of water? So now, let's see. Earlier it displaced this much water. Okay, so now what is that buoyant force if it had displaced this much water? So this is going to be a new volume of water. I'm going to say prime. Okay, I'm gonna try to squeeze it in here. If not, oh well. Okay, so we have a new volume of water. So our mass is going to be different. So MW, I'm going to say prime, is going to be the density of water still times the new volume of water. Okay, so you're going to plug in this same value here, so 10 to the third times our new volume, which is this guy here, 1 times 10 to the fifth. Okay, and that's our new mass. So I get 1 times 10 to the 8th kilograms, okay, as my new mass. So my buoyant force is going to be my new mass times G. So this number times 9.8. So we get 9.8 times 10 to the 8th newtons. Okay, so this is going to be our buoyant force that the water could exert on that steel. Okay, if it were shaped differently and displaced a different amount of water. Okay, different volume of water. Okay. Alright, so a bit more about Archimedes' principle, and then we have another example here. So there's this idea of specific gravity, and that's the ratio of the density of an object to a fluid, which is usually water. Okay. So that's kind of the idea that we were just looking at. And then an object appears to weigh less when it's submerged, and this is called the object's apparent weight. Okay, so when we submerge something into water, it seems to weigh less. You guys have probably noticed that when you're swimming in a pool, maybe, or a pond, or anything, a lake. Okay, you notice that you feel like your body weighs less than on land. It's easier to walk around, kind of a thing. Okay, so let's look at an example. It states the mass of an ancient Greek coin is determined in air to be 8.63 grams. When the coin is submerged in water, its apparent mass is 7.8 grams. Okay, we want to calculate its density given that water has a density of 1 gram per centimeter cube, and that effects caused by the wire suspending the coin are negligible. Okay, so, we want to calculate its density here. Okay, so we have two different masses. We have the mass in air and then its apparent mass underwater. Okay, remember that density is equal to mass over volume. Okay. Okay, so what we know, okay, is that we had the coin weigh so much outside in air versus the apparent mass. Okay, so what we'll do is we'll find that mass of the water, okay, or the lost mass. Okay, so we have 8.63 grams minus that mass that it reads in the water. Okay, and that's going to tell us the amount of mass that was sort of lost. Okay, so when it's submerged, it's weighing less. So let's see, 8.63 minus 7.8, that's going to be 0.83. 1.3 grams. Okay, so this is that mass of the water. And let's see. Using this mass, we can determine the volume of water that was displaced, and therefore the volume of the coin. Okay, so we're going to say the volume of water is going to be the same as the volume of the coin, which is going to be the density. Actually, it's going to be the mass over the density. Okay, so let's take that mass, 0.830 grams, and we're going to divide it by our density, which is 1.0 gram per centimeter cubed. Which is going to be 0.830 centimeters cubed. Okay, so now we have our mass of the coin, okay, and the volume of the coin. So we can find our density based on this information. It's going to be the mass divided by the volume of the coin. Okay. So we have, okay, 8.63 grams over our volume, which is 0.83 centimeters cubed. 8.63, and that is going to be 10.4, and this is in grams per centimeter cubed. Okay, so this is the density of that coin. Now I wanted to look at, that's what I was trying to do, see if our table here will tell us what type this is. So what type of substance is it? So 10.4 looks pretty close to silver going down this list. Yeah, so it looks like this coin is then going to be silver, which makes sense. Okay. All right, so moving on to a new idea, cohesion in liquids. So we're going to look at cohesion and adhesion. The first one has to do with cohesive forces, and these are attractive forces between molecules of the same type. So the same type of molecules, such as water, okay, so water molecules and so forth, okay, and this causes the surface of a liquid to contract to the smallest possible surface area, and that is called surface tension. Okay, and surface tension can actually be calculated through this equation here. This symbol here is a gamma, okay, and that's what surface tension is, okay, and that equals some force over a length, okay, and the gauge pressure is equal to 4 times that gamma over some r, some radius. Okay, so we'll use an example here. We want to calculate the gauge pressure inside a soap bubble with this radius using the surface tension of soapy water, and convert this pressure to mmHg. And we'll do this starting in our next video.